In part 1, what I did was to sketch a graph that is increasing. You can also sketch a graph that is increasing this way. So naming this as y is equal to fx before you continue to do the rest of the sketch is totally fine, as long as it is an increasing graph according to what the question says. So after I sketch this increasing graph, I'm going to look at this graph and see that, okay, for the right-hand side of the inequality, it actually represents the area that is between this graph that I've sketched, the x-axis, and from 0, x is equal to 0, to x is equal to 1. So the right-hand side, this definite integral here, represents the area of this region, all the way. Okay, so this is integration from 0 to 1 of fx dx. It is the exact area. And then if I were to compare it to the rectangles that I've just drawn here, okay, these rectangles here, if you're to look at the rectangles, I've intentionally drawn those rectangles such that the height is below the graph. Okay, I'm saying this because I could have drawn it in another way. I could have drawn the first rectangle with the height all the way up to here. Okay, this is one of the possible ways that I can draw the first rectangle. For the second rectangle, I can also draw it all the way up to here instead. The third rectangle, here. Okay, I could have drawn it this way, but if I were to draw the rectangles this way, that means if I were to sum the areas of the rectangles together, the sum of the areas of the rectangles will be bigger than the exact area between the graph and the x-axis between 0 to 1. But this is not what I want, because according to what the question says, we are supposed to create something that is less than the exact area. And this something here is going to be represented by the total area of the rectangles that I've just drawn, with the intention of drawing them below the graph this way and not above. Because if I can do it this way and drawing n numbers of rectangles from 0 to 1 will make sure that the width of the rectangles, if they were to be equal, it will be 1 divided by n number of rectangles. So the width are all going to be 1 over n all the way until the last rectangle here. It is still going to be equal to 1 over n. So for the first area, it is going to be base multiplied by height. And this height can be found by substituting 0 into fx. We can also write it as, instead of f0, f0 over n. So this is found here, 1 over n multiplied by f0 over n. So this represents the area of the first rectangle. For the second rectangle over here, for this second rectangle, we have a width of 1 over n also. And as for the height, it is substituting x as 1 over n. So the height with x as 1 over n is f of 1 over n. So it is this multiplied by this. So we have the area of the first rectangle seen here, area of the second rectangle seen here. If I were to continue with the pattern, we can go all the way up to the last rectangle with the width also at 1 over n, and the height is this. Okay, the height is this. So I'm going to substitute x as n minus 1 over n. So it will be f n minus 1 over n. And we see that happening here also. 1 over n multiplied by f n minus 1 over n. So this is the way that I can discuss about the meaning of what this left-hand side is representing. It represents the sum of the areas of the rectangle, and these rectangles are drawn below the graph. And that is why this sum is going to be less than the exact area between the graph, the x-axis, and x is equal to 0 and x is equal to 1. And henceforth, we can show that this series here, we can explain that this series here is less than this definite integral. What we need to do in part 2 is to find a relationship between this inequality and what we have explained in part 1. So I'm going to focus on the left-hand side of the inequality and rewriting it in this way. 1 over n, I'm going to leave it as it is because it is already matching to what we see in part 1. But this here, I'm going to rewrite. I'm going to rewrite this as e to the power of 2 times of 0 over n, because we see that this is f0 over n. And this, I'm going to write it as e to the power of 2 times of 1 over n. And this is f1 over n. Then we know that the next term here is f2 over n. So if I were to rewrite this, I can also go for a 2 times of 2 over n. And if I were to repeat this same pattern all the way until the very last term, it will be e to the power of 2 times of n minus 1 over n. And we are seeing this fn minus 1 over n here. So this gives us a hint of what is fx. Fx is going to be equal to e to the power of 2x. Because if I were to go for a f0 over n, it will be e to the power of 2, 0 over n, which is this term here. So this is f0 over n. If I were to go for f1 over n, it will be e to the power of 2, 1 over n, and that is this term over here. And all the way until the very last term, fn minus 1 over n, this is e to the power of 2, n minus 1 over n, which is this term here. So what we have seen now is this, where fx is replaced by what we are seeing here, which means that this is going to be less than integration from 0 to 1, and we have found fx. Fx is e to the power of 2x dx. So this expression here, according to the question, this expression here will always be less than this, which means that if this is less than k, the minimum k can go has to be defined by this definite integral. So this is how we are going to be quoting the least value for k, and that will be integration from 0 to 1 e to the power of 2x dx. Integrating this, it is going to be half e to the power of 2x from 0 to 1. So this will be half. Substituting 1 in, it will be e to the power of 2, minus substituting 0 in, it will be e to the power of 0, which is 1.